Okay, the topic I'll be discussing today is generating gravitational waves with generative adversarial networks. And the question that we're really trying to solve here is, can we use machine learning to generate unmodeled gravitational wave signals? Now, what do we mean by unmodeled? We know, for instance, gravitational waves coming from the collision of two black holes um, can be modeled using general relativity. As long as you have the prior parameters, you can then generate templates of waveforms, which you can then use in detections and things like that. But we expect there to be sources of gravitational waves that aren't so easily modeled by GR or any other sort of algorithm. So can we use machine learning to generate these unmodeled signals? And specifically, we're going to look at gravitational wave bursts because they have two characteristics that make our life a bit easier. They tend to have high amplitude, so they'll stick out above the inherent detector noise more, and they're of short duration, so we're not looking at large amounts of data here. They're typically shorter than a second. And I've shown here some 5 examples of what we're using in this work. So we have a sine Gaussian, a ring down, white noise burst, Gaussian pulse, and a short binary black hole merger. But I'm going to step back a little bit and talk about the actual model we're using for this. And it's generative adversarial networks, or GANs. And these are a form of generative machine learning that have been around since 2014, and they've been dramatically improved since then. They're really good at generating high fidelity images or text to speech or things like that. So for instance, these faces here are generated using a GAN, and they're of people who aren't real. So it's taken from this website, thispersondoesnotexist.com. Yeah, and these are all computer generated images from a GAN. It's quite impressive. So the idea of GANs is quite simple. I'll try to explain it as best I can here. It's basically a two-player game. Two neural networks are fighting against each other. The first player is a generator, and its task is to take in a random latent vector, it's called. So it's usually sampled from a Gaussian distribution, but just a bunch of numbers, which it then maps to its representation of whatever data it's trained on. So whether it be an image or a time series like this. The second player is called the discriminator, and its job is to take in either this fake sample or a real sample from the training set and determine where it came from. So it will label it as real or fake. It's basically a classifier. Because we know what we're feeding into the discriminator, either the real or the fake, we can label them. And let's say we label the real samples as 1 and the fake samples as 0. The discriminator then makes a prediction on that, and we can then compare it to what the label is. So, and after that we have the comparison that can calculate a loss. And in normal machine learning tradition, you then backpropagate that loss through the neural network, and that will update what's known as the weights, and that will make the discriminator better at classifying. In order to update the generator, you can do something similar, but you combine both the generator and the discriminator together, and then you backpropagate the loss throughout the entire network. And this happens one stage at a time. So you update the discriminator first, then you combine the model together, and then you update the generator weights. And hopefully, after lots of training and making sure that both models aren't better than the other, you should have a discriminator that gets good at classifying real and fake, and a generator that gets good at generating these fake data sets. Now, this is the original or vanilla GAN framework. The problem with this type of GAN, or one problem with this type of GAN, is that you have no control over what to generate. So when testing these sort of machine learning algorithms, a useful data set is the MNIST data set, which is a collection of handwritten numbers from 0 to 9. And if you were to train a GAN on them, it would generate these written digits, but you couldn't specify which one to do. Here comes in conditional GANs. So you can actually tell the generator, I want you to generate a 3, and it would generate a 3. So what we have for this conditional GAN is 2 inputs. We have still the same Z random vector, and also a class vector, which denotes the class. So the Z vector, the latent space, should give you, when you vary it, it should give you variation within the specific class. So say you have chosen to generate a picture of a dog, the Z vector, if you varied that, would give you maybe different breeds of a dog or different fur colors, etc. But you can also keep this latent vector fixed and then vary the class label. So say you wanted something that's between two classes, between a cat or dog. And here's an example of that. So we have a dog ball as well. So let's get back to gravitational waves. How are we going to label our data? So we have 5 different signals here. We're going to use one-hot encoding, which is just a binary value in one of the entries of your vector. So we have 5 classes, so it's a length 5 vector, and we just put in a 1 in one of the entries to signify the class. Hopefully that makes sense. And here are the parameters of the training data. As I said, these are burst signals, so they're going to quite short duration. They're all 1 second. The frequencies of the Gaussian, the burst, and the ringdown are 70 to 250 hertz. The decays are all the same, and we fix the central time epoch, or time of arrival, between 0.4 and 0.6 of the 1 second interval. And here are some GAN generations. So here we have fixed the class vector to be Gaussian, and then randomized the latent vector as inputs and made 6 waveforms. So we can see that the GAN has learned what a Gaussian is, and by varying this Z vector, we get different attributes of a Gaussian. So we have sort of lower frequency ones here, and higher frequency ones at the edges, and different decays and different start and end times. And of course, you can condition the GAN. You can then give inputs condition, the input condition to be ring down, Gaussian blip, white noise burst, or binary black hole. And these are all generations from the same GAN. That's all very well and good, but we want to generate unmodeled signals. So let's say we had a 2 class for demonstration purposes. We had a Gaussian and a ring down. You can interpolate between these 2 points in the space. So you start off with the 1, 0, and you end up with the 0, 1, and you interpolate between the 2 numbers. And you're hoping that these between classes will give you some sort of hybrid waveform between a Gaussian and a ring down. And that's what I've showed here. So I've kept the latent space fixed, and I'm interpolating between the 2 classes, and you can see it morphs relatively smoothly. You could stop it halfway through and see what we get. It's some sort of hybrid. So that's interpolating between 2 waveforms. We can take it a step further and see what we get if we mix all 5 waveforms together. And you can do it in different ways. You can just take a random number between 0 and 1 in each entry, which would be your sort of uniform way of doing things, or we can try a different way where we take the plane that intersects all classes. So I've tried to show this here. So we have 3 different classes for this example, and the plane that intersects all 3 classes is this triangle. So you can imagine the class space as being a cube in this 3-dimensional case, where each corner of the cube has a different is a different class, and you can walk along the plane that intersects all 3 of them. And you can generalize this to higher dimensions. So in our 5 hypercube class space, you would sample from what's known as a 4 simplex. And mathematically, we do that using the Dirichlet distribution. So what do you get when we sample from the simplex and just uniformly? So this first row here is our simplex sampling. So you'll notice that I've tried to put the vector labels above each panel. And because we're sampling from this hyperplane, all of the individual entries should add up to 1. And we get quite drastic waveforms here. The middle one looks mostly like a ring down here, but we do have 65% of it being in the ring down column. So, and in the bottom row we have just random numbers for each entry sampled uniformly, which gives a different flavor of unmodeledness. So we've shown that the GAN can generate these waveforms, and we've shown how to go between the classes and sample from them. One thing we might want to do is to test our generations to see, can they be distinguished from each other? And one way to do that is with a convolutional neural network. So the idea behind this is we generate some unmodeled signals using the GAN. We add Gaussian noise to it, we write in the data, and we generate an equal amount of noise-only signals. And we train a convolutional neural network to distinguish between noise with signal or noise only. And we could consider 3 cases. The modeled signals generated with the GAN, that'd be the corner points, the definitive classes, either Gaussian, either ring down, and so on and so on. And we can compare that to the unmodeled versions, those that are generated from the simplex, or those that are generated just randomly. And that will allow us to study the unmodeled signals by comparing these classes. And that's currently ongoing just now. But in summary, we've shown that GANs can be trained to generate 5 different signals. We developed a novel approach of generating unmodeled signals using a GAN. And we plan to show how these unmodeled signals can be used to train the CNN, and we can compare the different data sets. And we have a methods paper in preparation right now. But thank you for listening to this talk. Looking forward to some discussion later.